motherfucking music we crip to. Subscribe, nigga.
Hello, and welcome to Security Testing Android with Mercury. Before we get started, go for a little bit of audience participation because this is a conference, so we do need incessant polling of the audience. How many of you out there have written an Android app in the past? So, most of you. And how many of you considered the security of your application when you did so? Okay, a few, not nearly as many who have written an application. Before we get started, who am I and why am I here to talk to you about Android security? My name's Daniel Bradberry. I work at MWR InfoSecurity, which is a security consultancy firm based in the UK. And we're constantly testing our clients' requirements and keeping up to date with the latest technology. And one of the trends we saw was an emergence in mobile applications coming to us. So we thought we need to do something about this. We need to build a tool to help assess the security of Android applications. Because, to be perfectly honest, it wasn't great. So what are we going to look at today? Once this short introduction is over, we'll look at the security model on Android and how people get it wrong and introduce insecurity into their applications. We'll then introduce Mercury as a tool to help you test some of the most common things that people get wrong in their Android applications. And then we'll actually go through and we'll perform an assessment against a number of applications that you can download from the Google Play Store and demonstrate some vulnerabilities and how you can exploit them to extract information from these applications. Then we'll briefly touch on how we can extend Mercury and fit it into our development workflow to help us automate tasks. So, the security model on Android is actually pretty good compared to other mobile devices out there at the moment. It's Java, so most of your code runs in a Java virtual machine, which protects you from the normal kind of issues you get writing native code, such as buffer overflow vulnerabilities. And when it runs your code, it constrains it within a sandbox. Every app runs as a different user on the device, and those users have very granular permissions, both in terms of their access to the file system and access to other applications and system services. And the guys at Google have thought this through, and it does work very well. Whenever you want to interact with another application, you have to go through the central IPC mechanism on the Android device. And hopefully you've all written Android applications, so you know how this works. We won't spend too much time on it. But for the few of you who haven't, this is how applications interact with each other on Android. You share services with other applications by exporting endpoints. You can export an activity, which is a UI view that appears on the screen, a broadcast provider that allows you to send messages system-wide, content providers that allow access to the database and file system of your application, and services that do the background processing. There's then a component within the Android kernel itself called the binder, which routes messages called intents between all of these applications. So if application B wants to invoke an activity from application D, it sends an intent and it goes through, hits the correct endpoint, and it's up to application D to decide whether it wants to do it. And this has very granular permissions, and the binder checks them when any intent is sent. So, if we've got a good security model, why are Android applications vulnerable? There's a number of reasons that we commonly see. There are normal coding issues that you'd see in Java. Stuff where the application is just simply coded wrong. So you establish an SSL connection and you get a good secure connection, but you never actually validate the certificate from the remote server to make sure that it is the server you think you've established a secure connection to. Android also allows us to run native code on the device, which then opens us back up to all of the issues we have coding in C directly. Use of the SD card is common. Some people just don't seem to realize that the SD card is world readable to any application without any permission requirement. And we've seen backup applications that take a copy of all of the sensitive data from an application and write it out in clear text on the SD card, thus defeating the entire sandbox that was put in place for that protection. We very commonly see misuse of the inter-process communication, which is something we will focus on in this presentation. And believe it or not, apps shipping with debugging enabled. It's true, you can go onto the Google Play Store today, download applications, and they are debuggable. And you have to go out of your way to do that, so I don't know why that is the case. So, if people commonly get the IPC incorrect on Android, why is that the case? We've got nice IDEs, and it's quite easy to build this into your application. The problem is, it's not always immediately obvious what you're doing with IPC. Take a look at this snippet from an Android manifest file. We can see we declare an activity called main activity, and we export it. So we'd expect any application to be able to send an intent to invoke this activity. What about this snippet? All we've changed is we've removed exported true from that declaration. By default, exported is false, so we wouldn't expect to be able to invoke this from another application. But as it turns out, we can, because if you specify this intent filter, our activity is exported in any case. So simply reading your Android manifest file, you may not understand what is truly going on underneath. And there's a number of tools to help us do this. We've got the Android Asset Packaging tool, AAPT, which allows you to deconstruct the compiled Android manifest XML file from an APK file and look at what is really going on inside. And this will show you where where an activity or a content provider has been exported. You've also got the Android Debug Bridge, which allows you to interact with your application to test certain things out and see what happens. But what we were seeing increasingly was people writing a lot of custom scripts to test the security of their tools, which is time-consuming. We're testing a Java application running on a device. So we'd have to write a script, compile the script, wait for DEX to run, then push the result into APK to the device, then run it on the device, and then wait for the results to come back. Somehow, not quite sure how we're going to do that, because we can't just pop up a console on it and easily type away. So it was a bore to test Android applications, and maybe that's why people weren't doing it too well. So enter Mercury. Full disclosure, we build this tool, but it is open source, so we're not actually trying to sell it to you today. It's a security assessment framework that allows for dynamic analysis of applications whilst they're running on a device. And the way it's written, as we'll see later on, it allows for very rapid iteration of testing scripts. You don't have to wait for stuff to compile and push to a device and then run it and then collect the results. Furthermore, because of a few design decisions that we made early on, it's got some neat tricks it can do. So you don't have to have debugging enabled on a device to use this. So you can put it on your phone and just connect over Wi-Fi and test your app on it. And also, you can use this over the internet if you want to, but I wouldn't recommend it because this current version has no encryption or authorization, and it does essentially create a backdoor on your device. And as I said, it's open source. It's free software, so you can go to this link and you can download it and play with it. Although the version we'll be using in the demos today is the upcoming 2.0 release. So the interface might look slightly different, but all the same functionality is there. So, how does it work? We obviously need some way to interact with the running Dalvik VM on an Android device. And we achieve this with an agent, which is a small package of code that you deploy on your phone or into the emulator. And it sits there and it runs ideally with no permission, so it simulates what any application can do to your application. Although in reality, we do have to have one permission, which is the internet permission, so we can do networking. And then there's the console, which you run on your PC, and it allows you to interact with the agent and run bits of script against it. We've got two ways that we can run it. Both Mercury 1 and Mercury 2 support direct mode. So the console connects to a server exposed by the agent on the device. And this is really easy to set up. You just do an ADB port forward, hit a button, connect to localhost, and you have an active connection. We also support infrastructure mode from Mercury version 2, which allows both agents and consoles to connect to a central server, which is perfect if you don't have an ADB connection. Maybe your mobile phone is connected through a wireless internet connection and you don't know its IP address, or its IP address keeps changing because you use DHCP. And it will also allow you to traverse firewalls and NATs. And in this mode, you can actually have multiplayer support, so you can have one device and allow several users to come in and interact with it and test the applications on it. We'll be using infrastructure mode today purely because it's a little bit more stable in the current master build. So inside the Mercury console, we get a command line interface which allows us to interact with the phone through modules. So as we can see up there, there's a bunch of commands that we can run. So we can list out the available modules, we can run a module, we can pass a whole series of command line arguments to various modules to tell it what to do and to slightly fine-tune it to what we're going to do. And it also allows us to do some neat stuff like establish a shell on the remote device, so we can dispatch shell commands, again, without using ADB. This is just a sample of some of the modules that are available within the current version of Mercury. It's not an exhaustive list by any stretch of the imagination. That's why it runs out. It hasn't even got to the end of modules beginning with A. At last count, there were some 70 or 80 modules available. And as we ramp up towards the 2.0 release, that number is increasing quite rapidly. But that's enough theory. Let's actually see it in action. So what we have up here is we have the Mercury agents running in an Android emulator. We're running Android 4.1.2 here. It will work back to Froyo, I believe, 2.2, and we're working on getting the compatibility level right back down as low as we can. And what we can see here is we've just got a shell currently on my local machine. But I can ask the console to connect, and we can now see it has connected to the agent running in my emulator. It's printed out some information, so we can see that this device is an unknown manufacturer, the model is SDK, and the software version is 4.1.1. Okay, I was a minor version out. And now we can start to issue commands against it. So we can print out the basic help information, and we can see the commands available to us. We can list the available modules, and it will print all of those out. And then we can start to interact with the software running on the phone. So for something quite simple, we can run the package list module, which will go away, interrogate the package manager, and enumerate all packages installed on the device. So this is the emulator as it comes out of the box, with a few additional packages installed that we'll see come up at the end. We can also do some slightly more interesting things with it. So this is a particular favorite of mine, which searches applications on the device for secret codes. And these are the codes that you can type into the phone dialer that unlock hidden functionality. So it's like doing *#06# on a very old mobile, and it would show you the EMEA serial number of the phone. The same is true in Android. So we can see it's printed out at the top. If we go into the phone application running on here and type *#*# and then 36245 for email, and then ###. It's decided it's not going to work, so we clearly have the demo gods with us today. That would typically launch you into a secret debug menu for the email application, but for some reason it doesn't want to play ball. So, we've got the tool. How are we going to go about performing an assessment of our application? There's 4 stages that we should go from. To start off with, we need to identify the attack surface of our application, which is what is the potential surface that we have that we can actually find vulnerabilities in to exploit. We should then identify potential vectors in that surface and test them to discover if there are vulnerabilities present. And finally, we will come up with proof of concept exploits to determine the potential impact of that vulnerability and decide whether it warrants being fixed or not. So, what's the attack surface of a typical Android application? It depends on your application. Typically, it will be anything that you export to the IPC mechanism, so the activities, broadcast receivers, content providers, and services. It's also, if your app is marked as debuggable, it's kind of game over if your application is debuggable and you can just stop now. You can also widen the attack surface of your application by using shared user IDs, as we'll cover later. And this isn't an exhaustive list. It depends on your application. If you're using networking, then the network is an attack surface. If you're using NFC, then NFC is an attack surface. But these are common to all Android applications. So how are we going to get started? Mercury has a very handy command for us that will print out the attack surface of a package. So we can use the attack surface command, and then we'll run this against the built-in Android browser to start off with. And we can see that this package exports 6 activities, 4 broadcast receivers, and a content provider. No services. Which is okay, but it's not terribly useful just to know the numbers. We need to dig a little deeper. So let's take the activities that it exports. We can use the activity info command to show us what those are. We'll restrict it just to this package, because otherwise this will do it for every app installed in the emulator, which will take quite some time. And there we go. These are the 6 activities exported by the Android browser. And now we can interact with them. So I can't see anything in here that would actually constitute a security vulnerability, but for the sake of argument, let's try to start an activity. We specify the component, which is specified in 2 parts, the package name and the activity name, and then we pass a flag, activity new task, which should start a new task, just like you were sending the intent yourself. And the emulator launches the browser. Although, so we're now going to get a server error because I don't have an internet connection. So I said there's nothing in there that would constitute a security vulnerability, but we have seen examples where this actually allows authorization bypass in applications. So some applications export activities that they weren't expecting to. And by sending a crafted intent, you can launch an activity that you shouldn't have access to by default. An example of that although again, this is more a usability thing than a security vulnerability, is the National Rail Inquiries app from the UK. If I launch this, I get this infuriating splash screen that comes up for about 5 to 10 seconds before it actually lets me do anything in the application, which drives me nuts every time I want train times. So let's have a look in this package and see what activities it exports. uk.co.uk, not com. So we can see something interesting here. It actually exports a bunch of activities, and it differentiates between splash screen activity and home activity. So what I can do is come back to my command that allows me to launch an activity and maybe invoke the home screen directly. Whoops. And what do you know? I've bypassed the splash screen. As I said, I wouldn't consider this a security vulnerability because it's not allowed me access to anything I shouldn't have anyway, but we have seen examples of applications where that is the case, and you can jump through some login. The same is true for both broadcast receivers and services. If they're exported and you don't expect them to be exported, people can send information to them. A pattern we see quite commonly is this, and we specify my broadcast receiver, and we specify an intent filter for it, and we never once specify a permission to send that intent. And this can be critical. There is at least one application that you can get on a phone today where a vulnerability like this will allow you to install an arbitrary APK file on a device simply by sending a broadcast message saying, the APK is over there, would you install it, please? So let's move on from those because they're all much the same and look at content providers. We commonly see three problems with content providers. One is leaky providers, where they're just simply not protected and will quite happily hand over user data. And then we also see SQL injection in content providers backed by SQL-like databases, and directory traversal in content providers backed by the file system. One example of a leaky content provider was in Dropbox for Android up to version 1.1.4, and that's when they fixed it. If we look at this application, and look at the content providers this exports, we see that there is an authority, com Dropbox Android Dropbox exported, which has no permission required to read from that content provider and no permission required to write from it. We can't do anything with that directly. That is just the authority. We don't know if there are any path parts to it. But Mercury's got us covered there as well. Instead of running info, we'll ask it to find URIs in that package. This is now going to unpack the APK file and search the source for anything that looks like a content provider URL, so content://. And this has revealed 5 endpoints that the application uses. We don't need any permission to read anything, so it would make sense that we can look at what is in this metadata. So let's just ask it to list out the columns, because this is an emulator. It's not actually connected to Dropbox, so we won't see anything useful in there. But we can ask it for the columns in the metadata provider. And there we go. It's going to show us the file name of various files in that user's Dropbox folder. that user's Dropbox folder. This vulnerability was particularly bad because you could also write to that content provider. So by inserting a record in there, by sending an intent like this, and setting is the file modified locally to 1, we could actually trigger Dropbox to upload that file to the user's folder. So any file that Dropbox can read, we can upload to the user's public Dropbox folder, which, in this example, we've picked up the preferences database file, which contains the key pair that we need to log into that user's Dropbox. So we now have full read-write access on their Dropbox, and Dropbox thinks it's their phone. So I said, they fixed this in version 1.1.4. SQL injection is also incredibly common. If it's backed by an SQL database and people don't pass the input correctly and handle it correctly, then you're going to get exactly the same problem as if you were writing a website. And it can expose data that perhaps you shouldn't be able to see. There's an example of this in the Android core itself, which was reported and we were told doesn't constitute a vulnerability and will not be fixed. So, let's try this. Let's try and query a content provider. And we're going to query the settings secure content provider. And we're going to pass in a single quote mark as the projection. And Android has come back and given us an SQL exception. And it's also very handily shown us the query that it tried to execute. Select single quote mark from secure. This suggests to me that I can insert anything I want in there and change the query. Since I know it's SQLite, there'll be a table called SQLite master that will tell me the entire schema of the database. SQLite. 2 dashes makes the rest of the query a comment. It will go away, and after a couple of seconds, this will come back with the contents of the entire table, revealing to us every other table that we've gained access to. There we go. We can see a whole bunch of stuff in there. Some of it is indexes. It's not terribly interesting to us, but we've got access to a table called bookmarks and a table called Bluetooth devices that we probably shouldn't be able to see. Bluetooth devices in particular seems to contain details of every Bluetooth device your phone is connected to at the current time. Again, it's an emulator, it's not got Bluetooth, we can't really demo it that well. So that's the manual way to find SQL injection. But we're developers and we don't like to do things the manual way. We'd like to do things fast. So we have an SQL injection scanner module in Mercury that you can just pass a package to and it will go away and it will tell you if it's vulnerable to SQL injection. So we will run scanner provider injection and we'll run it on that same provider. And we can see it's come back and said there's injection in the projection part of that and also injection in the selection, where we pass in the where part of the query. Directory traversal is a very similar problem. It again stems from lack of proper input sanitization. But in this case, this will be content providers backed by the file system. So we have the function in Mercury to read from a content provider. And in this case, we're going to use the Open Intents File Manager because Once again, I wouldn't consider that a vulnerability per se. It's a file manager. It exists to allow you to read files. So we'll read from org, open intents, file manager. And now we'll pass the path part. So let's go back up a load of levels. Whoops. If we go back far enough, we'll ensure to hit the root, where it's a Linux system, so there should be an etc/host file. And yes, we have directory traversal. We can read that file. This means we can jump all over the system and read different files off. Again, that's the manual slow way. We also have a quick way. We have another scanner. So we can run a scanner provide a traversal on a package, and this will go away and retrieve the exact same information for us. Vulnerable providers. This is innocuous. I mean, it can read the etc/host file. Probably anyone can read the etc/host file. It's not terribly interesting. It says 127.0.0.1 is localhost. But this also allows me to read any file that this application can read that also exists within the sandbox. So I happen to know that this file manager has a database file that I shouldn't be able to read. Handy Mercury tip, you can type exclamation mark at the beginning of the line and it will pass anything else you type back into a shell on the device, so you can run Android shell commands. So if we try to ls/data/data org open intents file manager databases, we get permission denied. We shouldn't be able to read that folder. What we can do, however, is use the directory traversal in the file manager itself, because it definitely can read from that folder. So we can run read to the file manager, pass it the path to the database file we'd quite like to read, which I believe is called that, and we get an error, but it's an error because it's tried to copy binary data and print it out to a console, which just isn't going to work. And I wouldn't really want the entire binary SQL-like database file appearing here. And again, we have seen vulnerabilities in applications that purport to allow secure storage of your data, where exposed content providers allow directory traversal and allow you to pick up the unencrypted version of various files from their file system. Shared UIDs. They're rarely used. Where they are, it's normally for performance reasons. It allows your applications to interact with one another without going through the binder at the kernel level, so it's faster. What it also does is allow you to run your applications in the same process, which allows you to accumulate permissions of other processes. And it also widens your attack surface to any application that you run with the same user ID. Although you do have some protection, because this only works if your applications are signed with the same developer key, which means you should only be able to do it with your own applications. But if you are using shared user IDs, you need to consider everything as part of your attack surface and repeat this on every application. Again, Mercury can help us. So we can run a command to look for shared UIDs. And in this case, we'll just pass it UID 1000. It's a default system UID. It's used by the settings package. And this has come back and shown us that there are 5 packages that run with the shared UID. And these are all of the permissions that they're allowed to aggregate through the use of that ID. So if we were assessing the settings package, we would also have to assess each one of those other packages in turn. Debuggable apps is the other big one. It's fortunately less prevalent now than it used to be, but it is still the case, and I have recently downloaded from the Google Play Store. So, how can we do it? We've got a command information debuggable, which will go through the entire device and look for any package with the debuggable flag set. So we found 3 packages. We've got COM MWR Droid HG Agent, which is our Mercury client. It's a development project at the moment. That's kind of to be expected. We've also got the test package for it, again to be expected. But org Mozilla Firefox? Up until version 4, Firefox was shipping with the debug flag set in its package, which might not seem like a problem until you consider how the debugger on the Android device works. What happens when you start an application with debugging enabled on a phone is it starts to connect out to a port. So local TCP socket called JDWP control for Java debug wire. And normally, if you're connected and are debugging on your phone, so you've got USB debugging enabled, the ADBD service on your phone will be listening to that port and will intercept the connection, and then it will allow you to connect back to that application through ADB from your PC. But what happens if you don't have USB debugging enabled? Or you do, but the USB cable isn't connected? In that case, ADBD isn't running on your phone. And nothing is listening on the JDWP control socket. This allows any application that has the internet privilege to start up and start listening on that socket and intercept all incoming JDWP handshakes from debuggable apps. And then that app can complete the handshake, and it now has the ability to debug you, which means that app has the ability to execute code in your context. So the entire sandbox is rendered useless at this point, because this app can just say, yeah, that file, do you want to just copy that over here, copy it onto your SD card? I'll have that, please. Okay, so we've gone through very quickly some of the things that we can do with Mercury. There are dozens of other modules. There's scanners for known vulnerabilities. There's other ways to look at the data. But we're developers, and we don't like doing repetitive tasks, and we don't want to keep writing the same things in over and over again. Fortunately, Mercury is built in a way that makes it very extensible. So I mentioned before, you've got an agent and a console. The agent is an incredibly lightweight executor that uses client-side reflection to allow the console to execute any code it wants. The console is implemented in Python, which means you don't have the round trip of having to compile and push code to your device. You just write the code in Python, reload the module into the console, and execute it. And you can write near enough Java in Python, we'll see in a moment. So we can build tests for our own apps using this interface by writing our own modules. A module is really simple to write. It consists of a little metadata, just to tell Mercury, this is the module, this is what I want to appear as, this is where I want to be run from. and then an execute method that allows us to write Java code in Python. And because client-side reflection can be a little bit slow, we can also write some Java code, and then we can compile and dex that on the fly and push that down to the agent, load it into the running process, and execute that. So we can write short custom JavaScripts to execute as well. So this is possibly the simplest module in the whole of Mercury. It's the one that lists out all the packages installed on the device. We can see that it specifies its path as app_package, so it's app.package, and its class name is list, so we just run app_package list, and we execute this. And then in the execute method, this should look fairly familiar to you if you've tried interacting with the package manager on Android. We just get a reference to the package manager, using a nice shorthand so we don't have to get the application context first, and then get packages, and that returns an iterable collection of packages that we can access the package name field on and print out every one of the packages in order. It's really simple to do. As I said, this is all with reflection, so you can instantiate arbitrary classes off the Java system. So this sample module gets a new java.util.random and then proceeds to call methods on the object that is instantiated, possibly making it the world's most elaborate random number generator, because you have to go back around to someone's Android phone. Don't know, maybe you want slightly less entropy than is available on your desktop PC. But all methods and all fields on that class you've instantiated are accessible. You can also pick up class references themselves and call static methods and static properties. And class loading. As we said earlier, client-side reflection is slow, and it's too slow for some of the things we want to do, particularly reading files and operations like that. So we can take an APK file that has a small piece of Java source code in it, called myclass.apk, and load that class, telling it we want to get myClass out of that. And what Mercury will do is it will deliver this APK file to the agent, it will extract the class, and it will give you a reference back to it, which you can then pass to self.new, get a new instance of it, and interact with its properties and methods. So, to put this all together, here's a slightly more complex module. This is one of the first ones we ran. This is the module that pulls out secret codes. And as you can see, we're using all of the mechanisms here. So we load a class, we take the secret codes APK file, get the secret codes class from it, then iterate through all available packages, and as we reach each package, we pass it, the package object itself, to the find method on the secret codes class, which unpacks it and does all the very clever searching, and returns an array list that we can then iterate through and see how many secret codes we retrieved. Okay, to sum up, we do need to think about protecting our Android applications. Our smartphones are getting more and more powerful, and they're getting more and more data on them. And I'm sure most of you were in the Google keynote this morning when Tim Bray made his plea for people to consider security in their designs. And it's difficult, I'll admit that, but with the correct tools, we can definitely make our life easier. And for Android, Mercury is a good tool that allows you to find these vulnerabilities. Some of them it can find automatically, some of them you have to look yourself. But it will allow you to automate your security testing and interact with your Android apps. And moreover, interact with your Android apps with debugging disabled, so you can do this in their release configuration on a phone as it would be in your customer's hands. And just in case you didn't get the URL the first time, it is free open source software. You can download it from that link. Got a few minutes left if anyone has any questions. Can't see. Yes.
What about rooted phones? How will Mercury react to that?
So the question is, what about rooted phones and how will Mercury react? You can install Mercury on a rooted phone. It currently doesn't have anything in place to detect that because it doesn't care. If your phone is rooted, it's game over anyway, so you can't trust anything that you are told by the high-level APIs on a rooted device. And this is a problem that a number of software vendors have grappled with recently, and we are seeing increasingly ingenious ways coming up in software to try and detect if a phone has been rooted. But Mercury doesn't have that at the moment. Any more questions? Okay, well, I'll hang around at the front in case anyone does want to come down and ask something. It's too shy to do it at the moment. But other than that, just thank you for your attention, and I hope you enjoy what's left of DevOps.